I'm Alex Todd, and this summer I did research in Lexington with the Physics and Engineering Department at Washington & Lee. My research mainly focused on the material properties of polymers, but it wasn't solely limited to just that. I also spent a large portion of the summer learning the basics of chemistry and developing valuable lab skills. Before going further into my summer's work, I should provide a quick background of what the bigger goal of this research is. Eventually, scientists wanted to develop a revolutionary use of recycled plastic that can help engineers in construction. In other words, it's a step towards furthering green technology. These recycled plastics can be put to use in structures like bridges and railroad ties. One might ask, why plastics? And the answer is simple. There are advantages to using plastics over other materials like wood. When using plastics, engineers avoid the use of poisons that are often used to weatherproof wood to increase its lifespan. Plastics can last through critical weather conditions in both freezing cold and scorching hot temperatures. Recycled plastics are also degradation resistant. So, rather than placing them in a landfill to remain for the rest of eternity, they can be put to a more beneficial use. This research was a continuation off of my previous winter term's work. During the winter semester, I was mainly responsible for the visual imaging of plastics, determining properties based off what I saw in pictures rather than legitimate data. My job was to fracture plastic samples at the temperature of liquid nitrogen. Then, I was to insert them into a scanning electron microscope for an up-close visual analysis. I was to send the photographs that I took to a more experienced research team for deeper analysis at Rutgers University in New Jersey. This summer, I was responsible for a different approach to the project. I was going to be the one taking data from the tests and analyzing it myself. One step forward from what I'd been doing before, because now I was responsible for both mastering a theory and applying my own data into it. Because plastics are polymers, and my background in polymer science was lacking, I began this summer's research by reading. Textbooks, scientific papers, websites, whatever I could find. It was important for me to really get a grasp on the basic mechanical properties of polymers to investigate further into what plastics have best properties to serve as construction materials. When my background knowledge was strong enough, I began the physical research and testing. My project involved running compression tests on plastics that then produced data for analysis. My main focus concerned stress and strain on plastics under compression. In other words, studying how much an object deforms when a heavy force is loaded onto it. I was responsible for running compression tests on different plastic compositions to see how each responded to the loads, which reached up to 6,000 pounds. I wanted to explore to see which plastics deformed most, which ones remained sturdy under the load, which ones were most affected by heat, and which ones seemed unaffected completely by the combination of a heavy load and a hot environment. These tests on the plastics often took hours to complete, so I had plenty of time to focus on the theory behind what these tests could show me. I spent a great deal of time reading through one scientific paper, written by a research team consisting of Washington & Lee's own Dr. Ken Van Ness. I spent a couple hours each day trying to grasp exactly how the theory in this article worked. It took some time, but as the summer continued, I began to understand it more and more. I learned that there was a way to take the data from the shorter-term tests I had been running and apply it into an equation that would predict long-term deformation of a plastic under loads. This was revolutionary. If this theory were accurate, it would mean that engineers could see how strong a bridge would be standing 50 years into the future. A typical day in the lab this summer consisted of a morning arrival and immediate action. The machine I used to run these compression tests on, the plastic samples, is called an Instron machine. Each day, I would come into the lab and would run 2 or 3 tests on different plastics. Running a test involved the same 3 steps each time. First, it was necessary to measure the dimensions of the plastic sample. Then, I would insert the sample into the machine, run the test, and let a computer program called Blue Hill track the data, such as the loading being applied and the stress versus strain. And finally, when the test was complete, I would remove the plastic sample and measure it again to see if there were any noticeable differences in its dimension. All of this data was recorded into a spreadsheet in Microsoft Excel for future reference. As the summer furthered, I worked on organization of data and finding ways to chart and organize my work for future research students to view. I also created instruction manuals accompanied by pictures of the processes for those future students interested in the research study. My summer's research has been very rewarding. It's incredible how many different aspects an engineer has to look at before a material can be used in construction. Every single detail counts and everything must be considered because failure in doing so could be dangerous or even fatal. The tests I've been running must be performed thousands of times when considering materials used to construct bigger things like bridges, railroads, roads, and buildings. So, although I've been focusing in on how a material responds to heavy loads applied to it, there's so many other aspects that an engineer must put into consideration. So, in order to get a grasp on what sorts of other machines are out there, I took a week-long field trip to Rutgers University in Piscataway, New Jersey, where much of this data that I've been working on is being analyzed. I spent a full week learning about new machines that W&L does not have access to. I worked with different machines that could do things like measuring the rheology and flow of the polymers that make up the plastics, examining what happens to different polymers when heated or cooled, seeing the impact resistance of a plastic when it's hit at high force, and measuring the flexural strength of a plastic under a load. I also got to create plastic molds that I work with every day at Washington and Lee using an injection molding machine. This was the coolest process for me because I was able to individually take pipes that were recycled from underground and go through each step until a plastic mold was completed. I was responsible for cutting a pile of pipes using a bandsaw and then pelletizing them into a machine so they were small enough to be inserted into the molder. Watching a plastic be recycled into a reusable mold from beginning to end was pretty fascinating. In conclusion, I've learned that patience, understanding of accuracy, and confidence are crucial in performing these kinds of tests. Other scientists rely on the data produced to make a breakthrough, so everything I do is important. There's no room for me to slack or lose organization. Over the course of this summer, I've developed a steady work ethic, taken initiative, finished tasks, and collaborated with others to hopefully and finally reach results.